Hi, this is Random Code 2024. I'm Noah Mann. I'm the author of functionalj.io, which is a Java library that brings functional goodies to Java, allowing more functional style of code in Java. Today we'll handle the 8th puzzle. All the code discussed in this video and the link to all this will be in the video description. Let's get started. Day 8 puzzles, Resonant Collinearity. It involves rabbit conspiracy. We'll be given a set of antenna. Each antenna represented by letters. Antenna of the same letters are antenna of the same frequency. This antenna will resonate each other, create a spot where people will be more appetized to chocolate. We suspect that it's this rabbit that create this arrangement. So let's start from the top with this graph. We'll be given a set of antenna. In this case, I use color to represent different frequency. So we have two antenna with red and another one with green. And due to resonance, there will be this spot over here and this spot over here. I'll mark it with this 2 dot. Let's look at the code. Again, we make use of the helper position, and again we make use of the helper class position to check with the bound. This spot and this spot is in the collinear line with these two original antenna. So this is antenna, and these two spot is the spot that resonates with these two antenna. So at this point, if we don't do anything, there will be the increase of craving for chocolate. So we need to build antinode here, with marked by this darker dot. The resonance only happen with the antenna of the same frequency. So there is no resonance between the red antenna and the green antenna. However, if there's another green antenna like this, there will be resonance with this green antenna. So with this point and with this point, as you might notice, the green and the red antenna has the antinode at the same spot. We can reuse the antinode, so there's no need to build both of them. Let's look at the code. Here, once again, we make use of helper class position with the method is outer bound, which will be used later. Then we create a data class or struct antenna. And this is the main class, which get the input as a list of strings. So you can imagine that this is a list of strings. So the index of the input line is a row, and the characters that we are interested in will be a column. Once we get the list, we can extract the row count and the column count. Then we flat map it with index using this function. So to flat map with index is to map each of the line with the row. So we will get the row number and the line associated with the row. For each line, I match it with this regular expression that will search for everything that is not a dot. What we're going to get is a result, which is of a class regular expression map result. This is part of functional J. it's hold the match result, which contain things like a starting point of the match and the group in which it match. The start of the match is the column. So we have enough information to create a position. We have row and column. We can create a position of this antenna. We can get the symbol of this antenna from the first character of the matching group. So that is, for each line, we create multiple of this antenna because matches produce a regex result stream. So once we map, we get a regular stream of antenna. Because each line can have multiple antenna, we need to flat map it. So the result is a list of antenna. Once we get a list of antennas, we group them by their symbol. The result would be a map from characters to func list of antenna. Because we only need the list of antenna of the same symbol, we call value, and this value will be a func list of antenna. This is to cast the value to be of the exact type antenna, and then we call antinodes. So this will be a func list of antenna of the same type. So antenna of the same type will produce multiple antinodes. So what we got is multiple antinode for this, each of this in CDS. So we flat map it. The result of the flat map is a list of the antinodes position. We deduplicate them and then we count them. That is a general idea to solve this question. But how do we create antinode? Let's dig a little deeper. So if we go to the original graph, remind you again that this is an antenna. This is another antenna. These are the antinode we want to build, and these are another antinode we want to build. So how do we find this antinode? Well, the antinode is on the same line with both antenna, and the distance of this antinode to this antenna is the same distance between this antenna to this antenna. So what we're going to see, what we're going to look for is this distance. Once we get this distance, it will be the same distance between this and this. Okay, let's do some calculation. So this will be row 1, column 1, and this point will be row 2 and column 2. So this here, this guy will be row 2 minus row 1 and column 2 minus column 1. Okay, so because we want to use this vector here to add on top of this, so this point would be, because it add on top of the row 2, so it become row 2 and column 2 plus with row 2 minus row 1 and column 2 minus column 1, which is this guy. And the result would be, because there are 2 over row 2, so you get 2 row 2 minus row 1, comma, and 2 column 2 minus column 1. So this is how we find this antinode. And if we take a look at this as a first point, as is one here, and this is as a second point, we can calculate this antinode. But when we switch it, this become 2 and this become 1, we can find this antinode. So this way, we can just iterate to the antenna of the same frequency in a nest. So it go from point 1 to point 2, and then inside from point 1 to point 2. If the points are the same, we ignore. If the points are different, we just calculate the antinode. When it switch position, then we will get both of the antinode. So let's see at the code. This is a code to create antinodes from antenna, because we already grouped them for the same frequency, so we don't really care about frequency here anymore. And then we have the row count and the column count. Then we give this antenna to do a next loop, list 2, which means that it will do a next loop of the same list twice, and we will get the first and the second, because we don't want to do anything with the same node. If it's the same node, the antinode will be on the antenna. We don't really care, so we filter that out. And then we map the first and the second into an antinode. To create antinode, we get first and second, and we use that formula that we have earlier to calculate. The position of the antinode will be 2 times row of the second minus row of the first, and 2 times column of the second point minus the column of the first point. So for each pair, we get one position, right? So that's why we just do map. And after that, we make sure to exclude all the position that is out of bound. So the result of this antinode will be a list of position of antinodes that guarantee to be within the bounds. So it continues from here again. We deduplicate it, and then we count it. So what do you think of this? Is this code represent the concept of the solution? That is it for this part 1. So now part 2. Turn out that we forgot to account for the effect of the harmony, which state that it's not just only the one that go twice the distance, but it also go every position. So in this case, you see here, for these 2 antennas, it not only just generate this antinode, it also generate antinode of the same step all the way until it go out of bound. This is due to the resonant harmonic. So we need to account for that. Not only that, because the antenna itself is also within the same harmonic. So we need to account for that as well. With this new requirement, we take a look at the code. So for the part 2, we will adjust the antinodes. We first start the same, get the row count and the column count, and then we flat map with index to extract all antennas. What we get is a list of antennas. But because we're going to use them quite a lot, therefore it might be good to freeze it using the 2 immutable list here. Then we do the same with before to group by the antenna symbol, and then only use its value. And then we do a flat map to antinode. But this will work a little bit differently. We'll go in there to see. But we still create antinodes of each of the entries. We flat map it. So at this point, we will get a list of the position of the antinode. But because the position of the antenna itself, it can be the place for the antinode. So we need to append all of the position of the antenna into here. Then we deduplicate them and then count the size. To generate the antinode, because it can be multiple steps, not just only 2, so that means for a pair, first and second of the antenna, there can be multiple antinodes, and that is done by using range 1 to max. Max is just a number that large enough that should not cut off or anything. Then we use use the range here as a step. So we go from we can go from here and here to this one as a step 1, this 2 as step 2, and this 3 as step 3. So that's why we have to range from 1 to max, and then we create antinode for each pair and each step. Then we only accept until the pair is out of bound. So we will have multiple steps for a pair. So we map it, because this one is an integer, we map it to object, and then we use the step to call create antinode for the first and the second, now with the step. And that would mean for these two antenna, we will create this as the first one, this as a second, and this as a third. And we stop until we go out of bound. So that's what it is. We create an antinode for a pair, which is the first and the second, and the step, and then we calculate the next position. Look very similar to when we have only 2 steps. So we put 1 here, we get 2 times row, 2 times the second row minus first row, and so on. So that's a different from part 1 to part 2. Oh, you already see the code, so that's good. Again, what do you think? If this code more represent of the way you're thinking the flow will be, we extract antennas, we group them by symbol, and then for each of this antenna of the same symbol, we create antinodes for them. We flat map it, so we get the position of the antinode. Then we applied it. Then we append it with the antenna position, because antenna position can be the antenna, the ear can be the node. Then we just find the distance and then calculate size. That is it for part 2. All the code here and the relevant links will be in the description. If you like this video, you learned something, please click like. If you want your friends to learn about it too, please share. If you want to see more of it, please subscribe. And either way, I wish you have the rest of your day. Thank you for watching.